let us move on. Everybody, so far so good on instantiated models in Bayes. It's reasonably easy, yes? And now let's move on to a different kind of parametric model, which involves continuous variables and linear functions between them, the simplest possible model of this class. So these are called structural equation models, and the first example that's easy to show is with the same causal structure, education, income, and longevity, that we had in smoking, yellowed fingers, and lung cancer, but now we're going to parametrize it as a different kind of a quantitative relationships. So in a structural equation model, you have to take each variable and give it a structural equation. And the analog is that in the Bayes models, you had to take each variable and give it a conditional probability distribution, where the conditional part was on all its direct causes. And in the structural equation model, you have to take each variable and give it a structural equation where the inputs to that equation are the immediate causes, plus a noise term that introduces error or other factors that are wiggling besides the one that you had. So every variable x is now going to be a function of the immediate causes of x and this little term called epsilon x, which represents the other factors that we don't observe but that influence x. Okay? And what we need to do to get full stochasticity, or actually give a distribution over all the variables, is to put a distribution over the exogenous guys, and that will induce a distribution over the model variables that we care about. Okay? And so let's go through that a little more detailed. So suppose I have a causal graph, education, income, and longevity, and I do that into a path diagram, in which case now I've included these little error terms explicitly into the model, right? They're not boxed, which means they're not measured. They don't enter into the explicit, right, variables that we're doing, but they're nevertheless acting behind the scenes. And now these functions are fully deterministic. So it's not the probability of income that I'm setting the value of income as equal to beta 1 times the value of education plus the value of epsilon sub income. Right? So it's a little bit of a different idea, and that in the end puts probabilities over these guys that are boxed if I have probabilities over these exogenous error terms. Okay, so we're sort of taking a little bit of a different approach. The result is sort of the same. Okay, so these are the equations that would come out. Education is equal to its error term. Income is equal to its error term plus beta 1 times education. And longevity is beta 2 times education plus its error term. So these are the linear equations, right? These equations, in general, don't have to be linear. And there's a facility in Tetrad for making nonlinear equations, which is very powerful and very general. But the linear equations make things simple. The estimation theory is simple. The connection between the correlations and the model is simple. And so we're mostly going to stick to those. Okay. So in matrix form, the structural equations are just V equals beta V plus epsilon E, where these things are now matrices, not just single equations. In the exogenous distributions, right, we have to put a distribution over these error terms because they're the exogenous guys, and we have to put a joint distribution over them, and there's a single constraint that we have to follow, which is that for every pair of error terms, right, we make them pairwise independent. And then the second constraint, which is that the variance of these error terms is non-zero. They have to wiggle. They have to vary. And if they didn't vary, then you could have one measured variable fully determine, or a set of measured variables fully determine another measured variable, right, which is certainly a reasonable thing to do in many cases, but is very rare in actual data, and puts you into a different position mathematically. Yeah.
In general, do we need to have, is it sufficient to have pairwise independent for exogenous variables only, or do we need full independent?
Sorry?
In general case, not just 3 variable or unit SCMs, is it sufficient to have pairwise independence, or do we need joint independence?
Pairwise is enough in most of the classes of models. Some classes you need joint independence, but in all the ones I'm going to talk about, pairwise is enough. Sorry. In these distributions, I have 3 variables here. And what I've insisted upon is that for every pair of error terms, they're pairwise independent. I could insist that the joint distribution is fully independent, right, which is a little bit stronger than just pairwise independent. In the linear case, it doesn't matter. In the normal case, that's the same thing. And in general, it doesn't matter. Pairwise independence is enough. Right? There are some cases that's not true, but that's a sophisticated. Good? Yeah.
Unnecessarily Gaussian distribution, or don't have to?
The error terms, the question is, do the error terms have to have a Gaussian distribution? The answer is no. And for many, many years, the typical assumption was that the error terms were distributed like a bell curve, Gaussian, normal, right? But we found out recently, or not we, but other people, have found out that in fact, if the relationships are linear, but the error terms are non-normal, they have skew, then what we can learn is better. We can actually learn the fully unique directed graph that characterizes the causal relations. So that's actually an interesting development. It's just about maybe in the last 10 years, 15 years. The reason it makes sense to think of these variables that are error terms as Gaussian variables is they represent sort of an aggregate of all the other things that might influence those variables that we have not modeled, right? So if I look at longevity, and I say, what are all the factors that influence longevity, right? Education is one of them, but it probably is, right, mediated by something like how much health care, right, you know to get, how much food, the quality of your, et cetera, right? But there's lots of factors that influence your longevity. And if I have one term in which I aggregate all those factors together, and some of those factors are independent, when I keep adding those factors up into one term, right, by the central limit theorem, they're going to tend to be normally distributed. So it's actually quite a reasonable assumption saying that those things are normally distributed. So here's an example in which I do impose a normal distribution on the error terms, and I say jointly the error terms are distributed as normal with a mean of 0 and a variance-covariance matrix sigma squared. And then I impose this constraint by saying that sigma squared is diagonal, which means that all of the off-diagonal terms, which represent correlation between the error terms, are all 0, which is just another way to say they're pairwise independent. Okay? No variance is 0. Okay, so now I'm going to actually generate, I'm going to show you how you parameterize a graph into a structural equation model, right? And then put in actual numbers for the parameters. And then I'll ask you to do it. And finally, right, we're going to actually generate data. And in the middle, I'm going to show you a nice tool that makes a structural equation model format very easy.
What if the pairwise independence is not there, the actual data?
If I've left out a hidden common cause, right? So if I have, right, a model like that, and I assume that the error terms going into these two guys are independent, but there actually was a variable I've left out that's a common cause, that will, in effect, make the error terms correlated. Okay, so I'm going to do something that's a little bit weird to interpret, but it'll make a point that I'd like to make, so just humor me and let me do it, even though it doesn't make sense in some way, okay? So I have this graph, and it's smoking causes yellowed fingers and lung cancer, and I've interpreted it as a parametric model with discrete variables. There's no reason I can't interpret the same graph as a different parametric model, and I'm going to do that. So when I click it, again, I have this choice, but this time I'm going to choose SEM parametric model. And what you'll notice is that it does it for me automatically. It doesn't even ask me any questions. Why? It's because the SEM parametric model is so simple that even from the graph, I pretty much know all I need to parameterize it. So these beta 2, beta 1 terms are the linear coefficients, right, which I can attach to an edge. And what I haven't even put in here is the error terms, and I'm going to parameterize them as normal with mean 0 and variance that I get to set. And so if I want to see them, I go up to the parameters menu and say, show error terms. And then they come up, and there they are. And the error terms have a parameter that's the variance of that error term. So the parameters in this model are each error term has a variance. The mean is set to 0, so that's not a free parameter. And every time there's an edge, there's a coefficient that's attached to that edge. So this is a 5-parameter model. Okay? And in some sense, do I really care about the variance of the error terms? I don't really care about the variance of the error terms. And I'll get to that in a minute. So I say save. And in the same way I had to put in actual numbers for the parameters for a Bayes net in the conditional probability tables, if I put an instantiated model underneath the SEM and then double click on it, I get two choices, either a SEM or a standardized SEM. I'm going to choose standardized SEM because it's a very handy tool. And what it means, not an edge in this model. Well, I guess I can't do that. So I get these coefficients, ignore them, just say OK. And here's what I get when I open up the instantiated model. Each of the error terms has a variance, so that error term for yellowed fingers is distributed normally with a mean of 0 and a standard deviation of 1.24. The error term for lung cancer is distributed normally, right, with a mean of 0 and a variance, standard deviation of 1.69. Same thing here. And this coefficient is 0.6197, and that's 0.6721. Now the program has just deposited these numbers randomly to make your life easier because there's a lot of numbers sometimes to fill in. So what we do is we just let the program fill it in and then change them to numbers that you want that might make sense. So if I wanted to change the thing for smoking, I click on it and I get a dialog box. I might type in 0.5. And for this one, I might type in 0.7. So now I've changed the parameters in this model. If I say save, right, I now have that. And if I save this one, I have that. So this is the same causal graph. In this case, I've interpreted it as a Bayes network, in this case as a structural equation model. So the qualitative causation is the same. The parametric interpretation of that is completely different, right? And they're both equally as legitimate in some underlying sense. Okay, so the final step is once I've gotten an instantiated model, I then have all I need to generate data, right? So now I'm going to have, all right, the full side of the picture for how to represent and generate data. Yeah?
So in the STM model, the betas and M, the M stands for the mean?
Yes. You can set the mean or the intercept for the structural equations. So you can set the mean of a variable, and that's just a parameter you can set, right? Or you can set the intercept. That's a subtlety I'll get to a little bit later, but let's not worry about it now. Okay, so how do I generate data? Well, it's very easy. I click on the data node here. I put it on the workbench. And I connect each of these instantiated models to that data. And now I'm set up to go. And to actually generate data, pseudo-random generated data, I just double-click on the data box. And up it comes, and it says, what sample size would you like? Right? I'll say 50. And how many data sets do you want? That's just defaulted to 1, which is simple. I say OK, and then I get a random sample from that model in which I have 50 rows, right? And this is all being pulled from the distribution that that instantiated model encodes. So now if I do the same thing on the other side, structural equation model, right, it says 1,000. And now I get continuous data, right, where I can get all the way down to, right, 1,000 sample points, okay? So what you know is that these data sets, right, were pseudo-randomly sampled from that completely specified causal statistical model. So anything you want to do to test out estimation, inference, model fit, model generation, model search, et cetera, you can now do in this beautiful situation in which we know the truth, the gold standard that generates the data, right, which we never know in empirical research. So the reason we did this is because we wanted to know something about how reliable, right, the algorithms we were actually building were to discover something about the underlying causal structure that generated the data if all we had was the data. So it's just like you're in the world as a scientist, but now unlike being a scientist, you know the truth, right, from which the data was drawn, and so you can compare what you find against the truth and see if these algorithms have any worth at all. So it's basically the best possible circumstance for the algorithms, right? All the assumptions can be met, right, et cetera, and then let's see how they do, right? And then the test of how they're going to do in real life, it's a little bit worse because sometimes the assumptions might not be satisfied, right, and all sorts of other things might be problematic as well. Okay, so what I want you to do, right, and then just go ahead and break for lunch, right, is build a structural equation model, parametric model, and instantiated model, and then generate data from both your Bayes net and from your structural equation model, and just take a look at that data. I'll show you one more thing before I stop here and we'll go around and help you, is if you want, you can take a data set and you can go to the File menu and you can say Save Data, right? And then I pick the name, and then I can just say save that to my desktop, save. And then if I go look, right, my data should be somewhere, there it is, right? It's just a flat text file that has the data I generated with tetrad. So then I can take that text file and I can put it into any other program I like, right, R, SAS, Minitab, what have you, and then use that in your own analytical software, and again, see if your analytical software tools that you're comfortable with and you like, right, get you information about that data that you can then check in tetrad to see if it's true or not. Yeah. The molt is a reference. Joe, will you explain that? Yeah.
Yeah, I will explain. So that's for discrete data, you don't want to repeat a call, a row many times. So maybe you want to repeat it 5 times, you want to repeat an extra 10 times. So that molt is just the number of times you repeat each row.
Okay.
I have a question about the box for cloud saving. Is it capable to save the data on cloud or not?
If you have the cloud monitor.
Because it doesn't recognize any cloud in the subdirectories.
I don't know.
You have to say, and it seems that it
You
just
can save up the desktop and remove it to the cloud.
yes, so it cannot directly save the cloud.
Okay. Before we go around and help everybody generate their data, any questions in general?
What he said about mult?
The multiple. So, if I understand it correctly, then in the discrete case, for example, right, if you have a row, right, with a certain set of values, and you say, right, instead of just listing it 25 times, I just have multiple equals 25. That tells the software reading it back in how many multiples of that row to take as being in the data. So there's a value for that. Right. Okay, any questions in general about anything I covered this morning?
Is SEM not just a kind of Bayes net?
It's just a kind of Bayes net where the conditional probabilities, right, are constrained to be a certain form by the linear functions or the nonlinear functions. So really, it's just one instance of a Bayes net with a certain kind of conditional probability table, where if everything's normally distributed and it's linear functions, then the whole distribution is normal, and so all the conditional distribution is normal. So it's very, very well behaved and conjugate in the right ways. It's really easy to work with. Yeah.
So if my data is binary for like comp data, do you have that kind of notion for generalized linear model?
Yes. We have a generalized linear model where the transfer functions from the causes to the effects can be most any function you can actually represent. Yes. So usually in the field, structural equation models refer to linear functions, but the generalized structural equation model can be any function. And in fact, one of the things that's interesting is linear functions do not have any interactivity, right? So if I have two variables that cause a third, right, the function is additive. It doesn't matter what value this has. The influence of this guy is the same for any value of this. But that's not true in many cases in the world, and so if you want to express interactivity in a linear system, I have to generate another variable that might be the product of the first two, and then get the interactivity to be expressed in that. It might be easier to do it directly in a general SEM, which I will get to in the afternoon. But so far so good. We have the simple cases all done, and you've gotten all the way to generating data. So now you can play God, create your own models, generate data, right, and know from which the truth comes. Yes?
What the normal distribution is a big, assumption for the structural equation modeling.
Huge assumption, right. So it's the simplest, most constrained case in some sense. You need the fewest number of parameters to express the distribution, right? Everything's simple. And in the multinomial case on the other side, which I've showed you discrete, it's kind of the other way. It's the weakest, right? You're assuming nothing.
The assumption up above the data, it will reflect automatically in the data?
Yes. So for example, if I change the graph, right, or if I change so I can change the parameters. So I can take, right here, I can just say, I want the same exact graph and the same parametric model, but different values for the parameters. I can represent it that way, right? If I want to have a different parametric model up here, but if I want to have a different graph, right? Oops, I can do that. So I didn't tell you that, but if you click on something and it goes yellow, you've selected it. Then if you hit Control C, you've copied it. And if you hit Control V, you've pasted it. So that starts out. So if I want to say, gee, right, let's make this, and then I ramify all the way through, right, down with the parametric model, et cetera, my data will actually be generated from a different distribution in a very qualitatively different way. So that first graph entails, for any way I parameterize it, that yellowed fingers and lung cancer are independent conditional on smoking. Doesn't matter what parameters are, linear, discrete, general, it doesn't matter. That's always true. In the second graph, it's not always true, and it's in fact usually false. So that's a constraint that I can look at in the data and test. That's what I'll get to when we move to search, because that is the key to connecting these graphs to actually data constraints that I can test is independence and conditional independence, which is in fact a qualitative relationship. Yes and no. Okay, great. So go ahead and generate SEM, PMs and IMs, and generate data. We'll come around and help you. And then anytime you're feeling comfortable and you're good, you're free to go to lunch and just come back here at 1:30. All right.